In 1959, one of the most respected scientific journals in the world published a paper claiming Megalodon might have still been swimming in the ocean as recently as 11,000 years ago, not 23 million years ago, not 3 million years ago, 11,000. Close enough that early humans could have crossed paths with it. The claim came from actual physical evidence, tested using an accepted scientific method, published in the journal Nature. It took decades for researchers to fully dismantle it, and by then, the idea that Megalodon might not be completely gone had already spread far beyond the scientific community. To understand why that claim mattered so much, you have to understand what Megalodon actually was. A modern great white shark tops out around 20 feet. Megalodon is estimated to have reached at least 50 feet, with some estimates running as high as 65, roughly the length of a city bus. Its bite force has been calculated at around 180,000 newtons, more than 18 metric tons of pressure concentrated in its back teeth, compared to about 3 metric tons for Tyrannosaurus rex, and it's estimated to have weighed somewhere between 50 and 60 tons, heavier than several school buses stacked together. A shark that size, with a bite that powerful, surviving until just 11,000 years ago, wasn't a fringe theory when it was published. It was peer-reviewed science, and it terrified people for exactly the reason you'd expect. Megalodon wasn't a rare or localized animal either, which is part of what makes the uncertainty around it so striking. Its teeth have been recovered from Miocene and Pliocene sediment on every continent except Antarctica, spanning roughly 23 million years of ocean history before its extinction. By any measure, it was one of the most successful apex predators the planet has ever produced, and it left evidence of that success scattered across nearly the entire globe. Yet for an animal this widespread and this well documented, scientists still can't tell you with real confidence exactly how big it was, what shape its body actually took, or precisely when its story ended. The confusion around Megalodon's teeth actually predates modern science entirely. For centuries, large triangular fossil teeth found across the Mediterranean were believed to be the petrified tongues of snakes or dragons, ground into powder and sold as protection against poison. That misunderstanding held until 1667, when Danish anatomist Nicholas Steno dissected a shark's head and recognized the same tooth shape, correctly identifying the fossils as ancient shark teeth for the first time. If you're finding this interesting, be sure to subscribe to understand more DNA from the past. The problem starts with what actually survives of Megalodon in the fossil record. Sharks have skeletons made of cartilage, not bone, and cartilage almost never fossilizes. What's left behind is teeth, along with a small handful of vertebrae so rare that only 2 partial spinal columns have ever been recovered anywhere on Earth. Working from teeth alone, Swiss naturalist Louis Agassiz formally described the species in 1835. Because the teeth resembled an enormous version of a great white shark's, he classified the animal directly alongside the great white, naming it Carcharodon megalodon. That classification held for more than 150 years, and it shaped nearly every assumption scientists made about the animal's size, its shape, and how closely it was actually related to a shark still swimming in the ocean today. That perceived closeness to a living species is part of what made the 1959 claim so believable. 2 megalodon teeth recovered from the deep Pacific seafloor were examined by researcher Vladimir Chernetsky, who measured the thickness of a manganese dioxide crust that had slowly built up on the tooth surface over time. Manganese accumulates on the seafloor at a roughly known rate, so measuring crust thickness was treated as a legitimate way to estimate age, similar in principle to counting tree rings. Applied to those 2 teeth, the method produced an age of only about 11,000 to 24,000 years, a number wildly younger than teeth recovered from any confirmed geological layer. The paper ran in the same journal that would later publish some of the most important genetics research of the 20th century. The manganese dating method turned out to be far less reliable than researchers had assumed. Manganese doesn't accumulate at a constant, predictable rate across the seafloor. It depends on ocean currents, sediment disturbance, and how long a tooth simply sat exposed before being buried, meaning a tooth could pick up a thin crust for reasons that had nothing to do with when the animal actually died. A formal review published in the Cryptozoology Review in 1998 went back through the data and dismantled the claim entirely, tracing every reliably dated megalodon tooth back to sediment layers consistently millions of years old, with no credible evidence placing the species anywhere near the present. But by then, the idea that megalodon might still be out there had already taken hold in popular imagination, and versions of it still circulate today, more than 60 years after the method behind it was discredited. The myth didn't stay confined to old journal pages either. In 2013, the Discovery Channel opened Shark Week with a 2-hour special called Megalodon: The Monster Shark Lives, presented in documentary style with staged sightings and actors posing as researchers, only revealing at the very end that it had been dramatized. It drew 4.8 million viewers, the largest Shark Week audience at that point, and reignited the same still alive rumor the 1959 paper had first set loose, decades after the underlying science had already been settled. Even after the extinction date got sorted out, a second, deeper problem remained: figuring out what Megalodon actually looked like. Because the original classification placed it alongside the great white shark, researchers spent decades using great white body proportions to calculate Megalodon's size directly from tooth measurements. In 1996, researchers Michael Gottfried, Leonard Campagno, and Shelton Applegate published the field's most widely cited size estimate using exactly that method, calculating a maximum length of up to 66 feet. For years afterward, that figure became the standard number repeated across documentaries, museum placards, and textbooks. There was just one issue. Around the same time, closer analysis of tooth shape and serration patterns revealed that the great white shark's actual closest relative wasn't Megalodon at all. It was an extinct mako shark lineage called Isurus hastalis. The two species had simply evolved similar-looking teeth independently, both adapted for slicing through large marine prey, a case of convergent evolution rather than a close family relationship. Once that connection broke, Megalodon was formally reclassified out of the great white's genus entirely, moved into an extinct family called Otodontidae, and renamed Otodus Megalodon. That meant every size estimate built on great white proportions, including the 66-foot figure still repeated everywhere today, had been calculated by comparing Megalodon to the wrong animal from the very beginning. You'd expect that correction to settle the size question for good. It didn't. In 2020 and again in 2022, researcher Jack Cooper published 2- and 3-dimensional reconstructions of Megalodon's body, built around an extant great white shark as a reference template, reasoning that Megalodon likely shared the same warm-blooded physiology as living lamnid sharks. That model put an adult Megalodon at around 52 feet long and roughly 106,000 pounds, with a dorsal fin over 5 feet tall, concluding it could outswim any shark alive today. Marine biologist Philip Stearns disagreed. His team measured the only well-preserved Megalodon vertebral column ever found, a set of 141 vertebrae recovered from Belgium, directly against a great white's spine. The column alone came out to about 36 feet, considerably longer than the roughly 30 feet Cooper's great white-based model predicted for a column that size, meaning Megalodon's actual body was proportionally longer and more slender than the 2022 reconstruction, closer to an elongated cruising shark than a stretched-out great white. 2 peer-reviewed studies, published about a year apart, describe 2 visibly different animals, and marine biologists still haven't agreed on which one is closer to correct. Body shape wasn't the only open question. In 2023, geochemist Michael Griffiths led a team that finally tested whether Megalodon was warm-blooded at all, using a method called clumped isotope thermometry on fossilized tooth enamel. By measuring how certain carbon and oxygen isotopes bonded together inside the mineral structure, a pattern directly tied to the temperature at which the tooth formed inside a living animal. The team calculated Megalodon's average body temperature at around 81 degrees Fahrenheit, roughly 13 degrees warmer than the surrounding seawater. That confirmed regional endothermy, the same heat retention strategy used by living great whites and mako sharks, except Megalodon ran noticeably hotter than either modern species. That advantage likely let it swim faster and hunt across a far wider range of ocean temperatures. It also came at a steep metabolic cost, one several researchers now believe made Megalodon more vulnerable once its food supply eventually began to shrink. That same warm-blooded physiology likely powered the record-setting bite mentioned earlier. In 2008, biomechanist Stephen Rowe built a three-dimensional digital model of shark jaw mechanics at the University of New South Wales, calibrating it against a real 8-foot great white shark before scaling the model up to Megalodon's estimated size. The result, around 180,000 newtons of bite force, stood as the most powerful bite ever calculated for any animal at the time of publication. Fossilized whale bones bearing Megalodon bite marks show the shark targeting tail flukes and flippers specifically, disabling prey that size before delivering a killing bite, rather than attempting to swallow a whale whole in a single strike. Even Megalodon's early life stayed hidden until surprisingly recently. In 2010, researcher Catalina Pimiento led a University of Florida team that identified the first confirmed Megalodon nursery site in Panama's Gatun Formation, dating to around 10 million years ago. Of roughly 400 teeth collected from the site, the overwhelming majority belonged to juveniles between about 7 and 35 feet long, gathered in the same shallow, warm, prey-rich water rather than scattered randomly. Evidence that adult megalodons used specific coastal nurseries to raise their young somewhere safer than open ocean, the same basic strategy several shark species still rely on today. Subscribe to not miss the next one. None of this means Megalodon is still out there. Every one of these studies, the vertebral analysis, the isotope work, the bite force modeling, depends on fossilized remains that stopped forming millions of years ago. Megalodon was a warm water predator that lived near the ocean surface, close to the seals, whales, and large fish it needed to sustain a body that size and a metabolism that hot. Deep, cold water strips away exactly the conditions it depended on: little light, little prey, temperatures near freezing at the depths. Cryptid theories like to place it in the opposite of the warm, prey-rich surface waters every confirmed fossil site points back to. A predator built to run 7 to 13 degrees hotter than its surroundings, powering an 18-ton bite and a body more than 50 feet long, has no way to fuel itself somewhere that cold and that empty. It's exactly why claims placing Megalodon in somewhere like the Mariana Trench specifically don't hold up. The trench's deepest waters sit barely above freezing, under crushing pressure, with almost no large prey at that depth at all. The 1959 claim that once suggested otherwise has been thoroughly dismantled for decades. What keeps the mystery alive isn't a hidden population somewhere in the dark. It's that specialists are still actively disagreeing in papers published within the last few years about basic questions of size, shape, and metabolism, using nothing but teeth and a single spine from Belgium to work it out. None of this has slowed interest in the animal down in the present day either. Megalodon teeth are still surfacing constantly, dredged up by scallop trawlers off the American East Coast, pulled from riverbeds by recreational divers in South Carolina and Florida, and occasionally recovered from the same coastal sediment layers researchers rely on to test new dating and reconstruction methods. Each new tooth is a small chance to check the current models against fresh physical evidence, which is part of why the size and shape debate has stayed so active. The dataset keeps growing even while the fundamental questions remain unresolved. Even the extinction date keeps moving. In 2014, researchers Catalina Pimiento and Christopher Clements calculated Megalodon's extinction at roughly 2.6 million years ago, using the most complete fossil dataset available at the time. 5 years later, paleontologist Robert Boesenecker led a team back through that record and found most of the younger looking teeth had been reworked, eroded out of older rock, and redeposited into younger sediment, making them appear more recent than they actually were. Once those specimens were excluded, the real extinction date moved back a full million years to around 3,600,000 years ago, shifting the leading theory toward cooling oceans and a shrinking prey base rather than direct competition with the newly emerged great white shark. That's 6 separate corrections in under 2 centuries of formal study. The genus changed, the size estimate changed. The body shape is still being argued over by researchers working from the same handful of vertebrae. The warm-blooded discovery is barely 2 years old, and the extinction date currently taught in classrooms is itself less than 6 years old, a full million years off from the number used before it. Every fresh piece of evidence keeps forcing a fact that once felt settled to be thrown out and rebuilt from scratch. That's the real reason Megalodon still terrifies the people who study it for a living. Not because it might still be swimming somewhere in the dark, but because a predator this thoroughly documented can still rewrite its own story again and again, and there's no reason to believe the current version is the last one.